Hi there, my name is Tonya Esterhuizen. I'm a biostatistician from the Center for Evidence-Based Healthcare at Stellenbosch University. This podcast is around statistical error, power, and sample size calculation. I will start by outlining the main uses of statistics to us as researchers. Basically, firstly, statistics is a way of summarizing a collection of data in a clear and understandable way. So this could be thought about as describing the population. Next, we might want to draw inferences about a population from a sample, and this is referred to as estimation. And we might even want to go on and test hypotheses related to the population, which is hypothesis testing. Some of your studies might just revolve around describing the population and might not even go on to estimation or hypothesis testing. So sample sizes that are required for different purposes are calculated in different ways. Let's just recap quickly about how a sample is different from a population. A population is it consists of an entire set of objects or observations or scores that have something in common. You need to define your population in terms of person, place, and time, whereas a sample is a subset of the population. And since it's usually impractical to test every member of the population, we usually select a sample from the population using the best or most practical approach possible. Inferential statistics usually require that random sampling has been done. So if you've done something other than random sampling, particularly cluster sampling, you need to discuss that with your statistician in depth. If we were going on to test a hypothesis in our study, there are various steps that you have to follow. We usually start with a hypothesis about the population called the null hypothesis, and usually this is the hypothesis that we want to show is false. Then what we do is collect data and assess the viability of the null hypothesis in the light of the data that we've collected. If the data are very different from what would be expected under the assumption that the null hypothesis is true, then we reject the null hypothesis. However, if the data are not greatly different from what we'd expect under the null hypothesis, then we cannot reject the null hypothesis. For example, consider an experiment in which 10 subjects who performed a task after 24 hours of sleep deprivation scored 12 points lower than those who performed after a normal night's sleep. Could this 12-point difference have been real or due to chance? How much larger or smaller could the real population difference be than the 12 points found in the sample? These are the kind of questions that statistics will help you to answer, and will obviously depend a lot on your sample size. So the null hypothesis, usually shown as H0, is the hypothesis of no effect or difference or association. The one you want to show is false. For instance, the two means, if you've got two groups in your sample, you want to show that in the population those two means are actually equal. That's your null hypothesis. Whereas your alternative hypothesis would be the opposite of that, and it's usually that they are not equal. The steps that you would follow in hypothesis testing involve establishing the two hypotheses, the null and the alternative, to set the significance level, alpha, which we usually set in terms of medical statistics at 0.05, but that is up to you, the researcher, to set it. Then you would decide on what would be the appropriate statistical test to perform and calculate the test statistic. And from that you would generate a p-value, the probability of observing a difference as large as the difference that you did observe due to chance, and compare the p-value with alpha, the significance level. You would then make a decision regarding the null hypothesis around if the p-value is less than alpha, we reject the null hypothesis. If not, we fail to reject the null hypothesis. When the null hypothesis is rejected, the outcome is said to be statistically significant, but when it's not, it's said to be not statistically significant. The last step is then just to draw a conclusion regarding your original research hypothesis or aim based on your decision above. But remember that if we do not reject the null hypothesis, it's not the same as saying there is no effect or your experiment didn't work. Not necessarily the same. There's a really nice saying by Douglas Altman: absence of evidence is not evidence of absence. In other words, failing to show effect doesn't mean that there really isn't an effect in the population. It might just mean that your study was too small to detect such an effect. And as I said, that usually happens when the sample size is small, which is why sample size is so important to consider before you do your study. Consider another example, comparison of two diet programs, W and J. In the first instance, a small study compared the two diets, and the 95% confidence interval of the difference was from -5 to +10. Okay, so the 95% confidence interval means that in the population, we're 95% sure that the real difference between diet W and J was from 5 kilos less to 10 kilos more. So there was a wide range of possible differences, with zero difference or the null hypothesis being in the middle of that confidence interval, and therefore that study did not show any difference between the two diets. And then another study, which was a larger study, but compared the exact two diets, the exact same two diets in the exact same way, found a 95% confidence interval of the difference from -1 to +1. In other words, the difference between the two diets ranged from 1 kilo less lost to 1 kilo more. Still, 0 is in the 95% confidence interval, therefore 0 is amongst the range of possible differences in the population. So the second large study also didn't reject the null hypothesis. But which study would you be more inclined to believe? The researcher is entitled to say in this instance, in the large study, that there is no difference between the diets here, because the difference might actually, but whether there is a difference, it's not of clinical importance. Whereas in the small study, the 95% confidence interval included differences that were of clinical importance. Okay, so after you've done your hypothesis test and you've made your decision and conclusion around the null hypothesis based on your p-value, how sure are you that your decision is correct? Here in this table we can see that there are 4 options here. Well, firstly, your inference is based on your statistical test, whether or not you've rejected your null hypothesis. Okay, so the p-value that you get from your statistical test tells you whether you can or not reject the null hypothesis, and in the columns here is the truth. Either your null hypothesis is true or your null hypothesis is not true. So if the null hypothesis really is true, in other words that there is no difference between the groups, and we do not reject our null hypothesis, then we've made the correct decision. However, if our null hypothesis is really true and we do reject the null hypothesis, then clearly we've made an error, and that is called a type 1 error, and the probability of doing that is alpha. Now you will recognize alpha as 0.05, the level of statistical significance that we set. So that means that there's 5% chance of making a type 1 error every time you do a statistical test. We have to bear that in mind. If the null hypothesis is false, in other words, there really is a difference between the groups, and we do not reject our null hypothesis, then we have made a type 2 error. So that's the opposite of a type 1 error, and the probability of doing this is termed beta. So this is the one that we have to watch out for with sample size calculations, because if our sample size is too small, we can make a type 2 error because we will fail to find a difference, and there might really be a difference in the population. Just the last option is when you make a correct decision to reject a false null hypothesis, and that is the opposite of beta, or 1 minus beta, and that's called the power of the study. So the power is the probability of correctly rejecting a false null hypothesis. Here are just some definitions of those errors that I've spoken about before. You can have a read through that in your own time. So there's a trade-off between type 1 and type 2 errors. The more you guard yourself against one type of error, the more your chance of making the other type. Requiring very strong evidence to reject the null hypothesis makes it very unlikely that a true null hypothesis will be rejected. However, it increases the chance that a false null hypothesis will not be rejected, thus lowering the power. So we normally set our type 1 error rate at 0.05. Very seldom do we use 0.01, maybe for some clinical trials or something. It's harder to reject your null hypothesis at 0.01 level than it is at 0.05, and it also requires a higher sample size. Power. We spoke about power as the probability of rejecting the null hypothesis when it's false. And power is 1 minus beta. So whatever you set your power at, 1 minus that will be the probability of making a type 2 error. So either before you do your study, you should calculate either the power of the study with the sample size you've decided to use or is available for use, or calculate the required sample size for a specified level of power. If you cannot do that before the study for whatever reason, after doing the study you should conduct a retrospective power analysis to try and explain your results. So there's the two types of power analysis, a priori, beforehand, and post hoc, afterwards. Power is important because if the power of an experiment is low, then there'll be a good chance that the experiment will be inconclusive. Okay, so for instance, if you don't find a statistically significant result, you might have an inconclusive study. There are methods for estimating the power of an experiment before the experiment is conducted. If the power is too low, then the experiment can be redesigned by changing one of the factors that determine the power. Please remember, it's very unethical to do a study that's either under or overpowered, knowing about it beforehand. In reality, the sample size is usually determined by your resources and the availability of subjects. And then we can work backwards and determine, using a formula, how much of an effect we'll be able to detect with the given number of subjects that you can use. But if you find that the sample size is too small for a realistic effect size, then you should either abandon the study or change the objective and scope of the study, or try to source more participants, for instance by making a multi-centered study. The primary purpose of power analysis is to guide in the choice of sample size. Firstly, you specify the power that you wish to achieve, and then the sample size needed for that level of power can be estimated. The calculations depend on the size of the effect in the population. First and most difficult step in choosing a sample size is to estimate the effect size. In terms of how much power do you go for, 80% is a rough guide. You could have more than 80%, but I don't think you should have less than 80%, or 75% would be too low, definitely. Okay, so what affects the power? The variability in the data. If you are collecting a continuous variable and there's a lot of variability, a wide range of data leading to a very high standard deviation, that definitely affects your power, but there's nothing you can do about that. It is what it is. Alpha, or your significance level, will affect your power. The effect size affects your power. If you want to detect a very small minor difference, or a very tiny difference between groups, you're going to need a very big sample size. If you want to detect a large difference, if you think your difference is going to be very large, you can get away with a smaller sample size. And then of course your sample size is the main thing that affects the power. And all of these things have to be estimated before a power analysis can take place. Okay, so we spoke about variability. A higher variance or standard deviation will lower the power. There are ways of controlling or reducing your variance, but usually it's not possible. The alpha level we spoke about previously. The effect size, this is the most important thing that you guys have to know about. As I said, the higher the difference, the more power you'll have, or the smaller number of participants you'll be able to get away with. But you have to estimate that size of the difference that you want to be able to detect. You cannot leave that up to the statistician because it's a clinical question. What you should specify is the minimum difference of clinical importance that you would like your study to be able to detect. Sometimes you can get this from published studies that are similar to yours, where they've reported the means and standard deviations between the groups. Often the previous studies aren't similar enough to yours, and in that case you just need to use your best educated guess or that of your supervisor or an expert in the field to specify what would be a minimal difference that would make a clinically important difference. For example, a clinical trial to compare the effects of 2 analgesics on migraine sufferers asked how many patients would they need to conclude that drug A was superior to drug B. And they were asked the question, what do we mean by superior? Quantify it, put it into numbers. So the researchers decided that they would only consider clinical superiority if at least 70% of the patients preferred drug A to drug B. So they set their level of difference that they wanted to be able to detect. Then we said sample size also affects the power, and this is usually the only thing that can be controlled by the researcher. As the power increases, as the sample size increases. So choosing a sample size is a difficult decision. There's a trade-off between the gain in power and the time and cost of using large numbers of subjects. And sometimes your sample size is capped. Sometimes you only have a certain number that you can use. So these all need to be taken into consideration. Right, we know that there's a direct relationship between sample size and power, so which one must we estimate? Well, it depends which of those is fixed. If your sample size is fixed, then you have to solve for the power with that given sample size. If you can vary the number of subjects in your study, then you can set the power and say, I need to know how many participants to use with, for instance, 80% power. Okay, and then different study designs need different data that will go into calculation of the sample size. In a population survey, now this would just be your normal descriptive study that I spoke about earlier, where no hypothesis in particular is getting tested. You would need to know the expected frequency of the parameter in the population, as well as how close you want your estimate to be to the real population value, in other words, the precision. So the more precise you want it, the higher the sample size will have to be. In case control studies, we would need the frequency of the exposure, the expected frequency of the exposure in both cases and controls. In cohort studies or analytical cross-sectional studies or even randomized controlled trials, we would need to know the frequency of the outcome in the groups, in the exposed group and the unexposed group. Here are some resources that you can use for online freeware computer programs that can help you to calculate sample size online. I have referred to a list of formulae supplied, but of course it's not supplied in this podcast. And please refer to normal statistics textbooks for all the list of formulae, which are very standard. Thank you for listening. Goodbye.